is video 1 in the video series for Unit 5, Gas Laws. Take a moment to pause the video and read through the learning objectives that will be covered in this set of videos. The ideal gas concept is a model of the way that particles of gas behave at the microscopic level. We're going to take a look at the kinetic molecular theory of gases to help us explain gas behavior, and we're going to look at the relationship between this theory and the actual physical properties of gases. So the ideal gas concept is when a gas acts most gassy, I would say. And it's under a set of conditions in which we consider a gas to be ideal. One, when the gas particles are small, when the temperature is high so that they can be far apart from each other, and when the pressure is low. We'll review this again as we go throughout the lesson. So we can measure the following properties of a gas, and we look at temperature, we look at volume, we look at pressure, and we look at the mass. More specifically, we look at something what's called the molar mass, or not molar mass. We look at something called the number of moles, and that is related to the mass in that a gas that's 6.02 times 10 to the 23 particles of gas is equal to 1 mole of that gas. And depending on what the gas is, so let's say we were looking at hydrogen gas, that we look at the periodic table for every 1 hydrogen atom, it's 1.01 AMUs. We can also say that if we were looking at 1 mole of hydrogen, so this is just hydrogen on the periodic table, right? We would look at the value there, and we would say that it's 1.01 grams per mole. But because we're looking at hydrogen gas, and hydrogen gas itself has 2 atoms of hydrogen, or if we're looking at a whole mole of gas, then it would be 2 moles of hydrogen. So we would say 1.01 times 2 gives us 2.02 grams per mole of hydrogen gas. So essentially, we're measuring the amount of a gas, and we can look at the mass, or we can look at the number of moles. And remember, a mole of any substance is going to be 6.02 times 10 to the 23 particles. And for hydrogen gas, the mass of that 1 mole is 2.02 grams per mole. So 1 mole of hydrogen gas is going to be equal to 2.02 grams of hydrogen gas. That's why we can say about 2.02 grams per mole of hydrogen gas, right, is going to be equal to that 6.02 times 10 to the 23. So that was a way around the way explanation about this amount of a gas. And it's going to become important because we can change the amount of the gas, and it's also going to change the other properties of the gas. So let's take a look at the kinetic molecular theory of gases. Don't forget that every time you see these clickable links in a PowerPoint lecture, that you can click on these links and they will take you to other websites that give you a little bit more information about the content on the slide. So what is the kinetic molecular theory of gases? Well, the first postulate is that gases are made up of small atoms or molecules that are in constant random motion, meaning that particles of a gas are always going to be at rapid random motion. The distance between these particles is very large compared to the size of the individual atoms or molecules. So I'll say, when we're talking about atoms or molecules, I'm going to say particles. because it can represent either atoms or molecules. So for a gas, the distance between these particles is really, really far apart. And the distance between them is much, much, much larger than the size of those particles themselves. So most of the sample of a gas is empty space. And because the particles are so far away from each other, they behave independently. And what that means is that they're so far apart that there are no attractive or repulsive forces between them. They act independently of each other. Each gas particle acts independently of every other gas particle in the sample. Gas particles collide with each other and the walls of the container without losing energy. And these are elastic collisions. So an elastic collision is something like this, where when two particles come together, they bounce right back off of each other. That's an elastic collision where no energy is lost. If I have one particle that is moving to another particle and the particle falls over, that would be a non-elastic collision where the energy is transferred. So in a elastic collision, there is no transfer of energy from one atom or particle to another. The last postulate, number 5, is that the average kinetic energy of the atoms or molecules or the particles of gas increases or decreases in proportion to the absolute temperature. And so what this means is that whenever we're looking at doing any calculations with these gases, and we'll look at gas laws, we're always going to use the Kelvin's temperature scale. And we use that because the absolute temperature is related to the average velocity of the gas particles. And the velocity is directly related to the kinetic energy. Celsius is not related to the velocity. And so what we know is that the smaller the gas particles, the faster they can move. The larger the gas particles, the slower they move, right? And so the mass of one gas particle is going to be related to how fast it's going to move. The smaller the mass, the smaller the mass, the faster it moves. The larger the mass, the slower it moves. And what we know is that as the temperature goes up, the particle speed goes up. So the particles of a gas are going to speed up, and the temperature of that gas also, when the temperature of that gas increases. So we can use the kinetic molecular theory of gases to explain a number of gas behaviors, right? So you know that gases are easily compressible, that you can squeeze a lot of gas into a smaller space because the gas particles are mostly empty space so that they can be squeezed together. You know that a gas will expand to fill any available volume, right? And the reason why is because each gas particle is moving independently of others, and they can move freely with enough energy to overcome any attractive forces. Gases have low density. Well, the reason why is because it's mostly empty space. And if we remember what density is mass per unit volume. So if I have a volume, but there's very few gas molecules in that volume, then it's going to be low density. But if I squeeze the volume, those particles get closer and closer together. And so the density of the gas will increase. If I squeeze the volume, those particles, and it's the same amount of gas, the particles will get closer and closer together. Now, if the temperature is high, right, for gas particles and they're moving around much faster, right, then that would decrease the density because they want to get farther and farther away from each other, right? Whereas if the temperature is low, then the density would be higher because they get closer together. Now, you know this to be true, that if you're in a room where, it's colder closer to the floor and it's warmer closer to the ceiling, well, cool air sinks, warm air rises. So I want you to know that this is probably the most chemistry that you know, like just from your own personal experience, that you have experienced gases behaving like gases. You might not have known that you knew this information, but you might not have known what the gas laws, what the names were, but you can definitely describe gas behavior based on your own experience. The kinetic molecular theory of gases also explains why gases readily diffuse through each other. And the reason being is that there's continuous motion. And because there's a large space in between gas particles, they can diffuse easily. Have you ever been on the subway or on a train or in a small space and you smell something and you wonder, where did that go? Or have you been the one who let something go in a small space and you're hoping that it doesn't get too far, but someone on the other end of the room said, oh, it smells funny in here. Why? That's because gases readily diffuse through each other. Something to think about. A little chuckle. Gases also exert pressure on their containers. And the reason why this is because the collisions that the gases have with their container walls provides that pressure. And I mentioned a little while ago that gases behave most ideally when they are in where there's low pressure exerted on them and high temperature. So that means that if there's low pressure being exerted on a sample of gas, then that gas has enough room to expand and it can move freely and be independent of other gas molecules, right? If the temperature is high, it can move really fast. So let me ask you something. Butane is a gas at room temperature, but how come they're a liquid in a lighter? Because they're compressed into that very small volume. And so the gas particles, they get really, really close together, and then they end up having those interactive forces between them, which causes them to be a liquid. Here we have an example of gas diffusion. We have hydrogen chloride gas here on the left side and ammonia gas here on the right side. And notice that because ammonia is smaller, its molar mass is smaller, right? The mass of 6.02 times 10 to the 23 ammonia molecules is much less than the mass of 6.02 times 10 to the 23 particles of hydrogen chloride gas. So notice that at the end of the experiment that the ammonia has moved farther down the tube than the hydrogen chloride. So the hydrogen chloride gas does move a bit, but because it's much larger, it is heavier, it moves slower. So ammonia diffused farther in the same amount of time because the lighter the gas is or the less heavy the gas is, the faster it moves.